Okay, so today we will discuss about three numerical method that is roots of high degree equation. Yeah, um, we will start with bisection method and then a Newton method, and we will continue with a fixed point iteration, and then we will perform the calculation using Python. Yeah. Okay, before we jump to Python, I will give you the explanation about bisection method. Okay, so these are three methods that we will discuss for today. Okay, let us start with bisection method. So bisection method basically start from the intermediate value theorem. Okay, so in intermediate value theorem in calculus, we already know this. Let f be a function defined on closed interval a, b, and let w be a number between fa and fb. Yeah, so w is between the range of f. Yeah, and if f continues on ab, so this is the term. Yeah, the term that must be satisfied. If f is continuous on ab, then there is at least one number c between a and b such that fc equal w. Yeah, so this is the basic or the starting point, yeah, from the bisection method. So this w can be anything, can be any number, so, as long as this w between fa and fb. Yeah. Okay, so basically it's not only for zero, as long as w between a and b, therefore uh, we can have the fact from of this theorem. Okay, now let us apply this method or this theorem to find a root, yeah, or to find a solution of fx equals 0, like we have before. Okay, so what is bisection? Suppose f is a continuous function. So this is the main term, yeah, that must be satisfied. And then, yeah, it's defined on interval a and b with fa and fb with the opposite signs. So in here, fa must be positive, fb negative, or vice versa, yeah, fa negative or fb positive. Therefore, because the graph is continuous, then it must be intersect with the x-axis. Yeah. Okay, so this is the case. Yeah, it's guaranteed that our problem has a solution. Okay, it will guarantee that our problem has a solution. Yeah, so this is the case. Yeah, and this is A, for example, and this is B. So FA positive and FB negative. Yeah, or you can have the following as well: X, Y, or you can also like this. This is A, B, and this is FA, and this is FB. FA is negative, FB is positive. Yeah, and this is the range. This is the range of the function. Yeah, from something to something. Okay, and this is the point that we want to find. Yeah, the point C such that FC equal 0. Yeah, also in here, FC equal 0. Okay, next. The intermediate value theorem implies that a number P exists, or in our case C, yeah, in AB with FP equals 0. Okay, so this is the root, yeah. This point P or this value P is called root of F or akar, ya, akar dari fungsi F. Okay, So this procedure will work when there is more than one root. Yeah, so it could be more than one between A and B. Okay, so it does not guarantee it always be one. Yeah. So when this situation is satisfied, FA and FB has the opposite sign, at least we have 1 point, yeah, at least, but it will have more than one actually. It could have more than 1 point. If there are more than 1 point that satisfied, the graph could be like this. Yeah, so the graph could be like this. Yeah, so this is A, this is B. Okay, and then this is FA is positive and FB is negative. So it satisfied this requirement. Yeah, FA and FB has opposite sign, but it has more than one root. Yeah, this is, let's say, C1, C2, C3, and C4. Okay, yeah, it could be like this. Okay, therefore, what our aim is to find the following all of this point, yeah, such that FCI equals 0 for I 1, 2, 3, 4. Yeah. Okay. But that's okay. Yeah, that's not the problem. So the important thing that we need to satisfy is this requirement. Yeah, FA and FB must have opposite sign. As long as the function is continuous, then we can guarantee that the root lies in the interval, yeah, A until B. Okay, let's continue. Okay, so this method calls for a repeating halving or bisection of subinterval of AB. And at each step, locating the half containing P. So actually, this bisection is divide the interval AB and trace where the point C is or the point P is between A and B. Okay, so the procedure work like this. Let's continue. We start with interval, yeah, A until B, and then find P1. So this P1 is the middle point, yeah, between A and B. Therefore, you calculate like this. You add A plus B divided by 2, and then you have P1. Okay, so now, yeah, okay, so let me give you illustration. Suppose this is the case, yeah. Suppose this is the case. This is A, this is B. And then you find the point P1. For the first step, you find the point P1, which is A plus B divided by 2. Let's say this is the point P1, okay? Okay, so you see here, FA is positive and FB is negative, right? After you find P1, you check again, what is the value of FP1? Is it positive or negative? Okay, so because let's say in this case, because P1 lies below, it means that FP1 is negative. Therefore, the point containing the root is in the interval of A and P1. Yeah, and this one does not contain the root that we want to find, right? Because look at this, the graph does not intersect the x-axis in here. Okay, so this is the point C or point P that we want to find. Yeah. Okay, after you have FP1 negative, FA positive, so it satisfies again the opposite sign, right? Then you do the steps again to find the second point. Yeah, second point P2. P2 is A plus P1 divided by 2. Yeah. Okay, so then let's say P2 lies in here. Okay, P2. And then you check again, what is the sign of P2? FP2, yeah, obviously it's positive, right? In this case. And then Now you remove the point A, so you don't consider interval A until P2 again. But now we consider the interval, our A1, now our A1 become P2, and our B1, yeah. So because this is the second iteration, yeah, it become A2, and B2 equal to P1 in this case, right? Because it satisfies the opposite sign again. Yeah, as you can see, now our interval becomes smaller and smaller, which contain the root P. Yeah, you do the same again. Find P3, okay? Find P3, which is P1 plus P2 divided by 2, yeah? Then you will have this following, right? This is P3, okay? And then you check again, what is the sign of P3? Yeah, yeah, in this case, it is positive. And then now our interval is P3 until P1, okay? You do the same, it will converge, yeah, until it is converged to our point P, yeah? So by continuing this procedure, our P will converge, yeah, our Pn converge to P. So we will create, yeah, we will create a sequence, yeah, we will create a sequence of point. Let's say this is Pn that will converge to the point P. Okay, yeah, that is the procedure of bisection. That is, we divide the interval, yeah, such that the interval becomes smaller and smaller, and then we can find the point of the root, yeah, that we want to find. Okay, you get it? Yeah, so that's the procedure. Yeah, so this is the procedure. You set in here, we want to find fp1 equals 0. Yeah, so this is the case. Yeah, this is the algorithm. If you you calculate this and then you check, yeah, if p1 equals 0, then p1 is the root, or this is the point that we are desired to find. But if p1 is not positive, then fp1 has the same sign, either fa1 or fb1. Yeah, so at first we have fa and fb in the opposite sign. After we calculate p1, yeah, we check what is the sign of fp1, and then it could be same sign with fa1 or fb1. Yeah, so if fp1 and fa1 have the same sign, yeah, then we remove a1. Okay, if fp1 and fa1 have the same sign, we remove a1. Therefore, the root or the point that we want to find is in the interval p1 until b1. Okay, then the next step is set a2 equal p1, yeah, and b2 equal b1. Otherwise, if fp1 and okay, so this is not a1 actually, yeah, so b1. Okay, I will revise this. If fp1 and fb1 have opposite sign, then we remove b1. Then the interval that contain the point P is A1 until P1. Okay. The next step, set A2 equal A1, yeah, in here, and B2 equal P1. So this process goes on and on and on until we arrive, yeah, or we converge to the value. Okay, we converge to value of P. And it could be long, yeah, it could be really long process. Okay, it depends on the problem. If the problem is simple, probably it's only take like 5 iteration. But if the problem is difficult or more complicated, yeah, it could take more than 10 iteration. And of course that is not possible, or if you are using your hand, it will take a long time. Therefore, we will use software, program, to create the algorithm such that the program will do the iteration for us. So we will until we only work with the algorithm, then we will see the result. Yeah. Okay, you get it until here? So this is the process, yeah. Like we see before, we start with A1 and B1. A1 equal A and B1 equal B. So this is the interval. Okay, the first step that you need to do is find the interval A, B such that the value of F has the opposite sign, yeah. Find the interval A and B such that the value of F has the opposite sign. Okay, and then after that, after you find the value of A and B, you can apply the following. Set A1 equal A and B1 equal B and find P1. P1 is A1 plus B1 divided by 2. And then you can check again, yeah, what is the sign of FP1? Is the FP1 positive or negative? Or which one is the same, has which value that has the same sign with FP1? Yeah, and then you remove 1 point, and then this P1 could become A2 or could become B2. Yeah. Okay, so this process continues, yeah, until you find the value of P in here. Okay, that's the procedure of bisection. Yeah, it will divide until the interval will become smaller and smaller until we converge to this value. Okay, so this is the algorithm. Yeah, it's called pseudocode. Okay, I will show you this later. Yeah, with Python. Actually, it can be applied not only in Python but into all the programming language. Yeah, whether it is in C or in C++ or Java or anything. But the simplest way is to use Python, yeah, because Python does not need any requirement like C++, yeah, or C that is more complicated, but it's just, it can be directly translated into the programming language, yeah. And also with MATLAB, it will be more easier because we don't have to import any package. It's already there, yeah. Okay, so let's continue. Let's see the example before. Example 1 show that fx x cubic plus 4x squared minus 10 has a root in 1,2. So in here, a is 1 and b is 2, yeah. And use the bisection method to determine an approximation to the root that is accurate at least within 10 power minus 4. Okay, so first what you need to do is to show that this function has root, yeah, has a root. So look at this. This is a polynomial of degree 3, right? Polynomial derajat 3. So it means that at most, paling banyak, ya, this polynomial has 3 root. Jadi paling banyak dia mempunyai 3 akar, ya. There are 3 value, C1, C2, and C3, such that FC for each C equals 0. Yeah. Okay. We don't have to find all of the points. Yeah. We don't have to find all of the C, all of those 3, but we just find the point. Yeah. 1 point. That's enough. Okay. So and this one, the problem is limited, yeah, to this interval. Can you show this? Okay, what should you do? First, we need to guarantee that this function is continuous. Okay, So this function is continuous because this is the polynomial function. Yeah, all the polynomial function is continuous. So there is no problem with this. It's different with trigonometric. Yeah, not all trigonometric function is continuous. For example, tangen, yeah, is not continuous, and also the continuous or the trigonometric function that is continuous only sin and cos. Beside sin and cos, other than sin and cos is not continuous. Yeah, for example, tangent function or tangent function is not continuous in the point uh, 90 degree, yeah, or v over 2 and 270 degree, right? Yeah, and multiplication of that. Yeah, so that's the problem with trigonometry. Yeah, so doesn't have it couldn't have a root, yeah, if that is the problem. Okay, so because we are dealing with polynomial, so it is safe, yeah. First, because fx is polynomial of degree 3, then fx is continuous. Yeah, in fact, the polynomial is the nice function. Yeah, it's a nice function. Yeah, because this function is continuous and differentiable. Yeah, so this polynomial differentiable infinitely many times. Yeah, so it doesn't have degree of differentiability. So the degree of differentiability is infinite. You can differentiate this function as many as you wish. Yeah, that is the advantage of polynomial function. Therefore, it always used in a numerical method. Yeah, so that we can approximate any function using polynomial function because of this nice property. Yeah, the property of polynomial is it always continues and infinitely many differentiability. Yeah, so Pn, yeah, so Pnx belong to the space, yeah, C infinity AB. So what does it mean? It means that this is the set of function, yeah. So if you see in the book this kind of notation, this is a set of function. Imagine that you have a set, but the member of that set is functions, many functions, yeah. But in here, C denote continuity. It means that this polynomial belong to continuous function that has infinitely many time differentiability. Yeah, infinitely differentiability. Okay, that is the nice. It's really nice function. Okay, now the next step after it's continuous, then we can check the value. Yeah, or the what is the we need to check whether it has the opposite sign. Okay, consider f1. So what is the value of f1? 1 cubic plus 1 square minus 10. Result is minus 5, yeah? It's negative. And f2 is 2 cubic plus 4 times 2 square minus 10. So the result is 8 plus 16, yeah? 24. 24 minus 10. 24 minus 10 is 14. Okay, it's positive. So it is satisfied, right? F1 is negative, F2 is positive. Then we have opposite sign. Yeah, because, okay, now because F1 negative and F2 positive, then by the intermediate value theorem, there is a value, there is C, yeah. We do not know what is the value of C. There is C, element of 1 until 2, yeah, belong to the interval 1 until 2. Okay, so it's not like this. It should be like this. Okay, such that FC equals 0. Okay, so the intermediate value theorem guarantee that this function or this polynomial function has root between 1 until 2. Okay, now let us find the value of C, how the bisection method work. Yeah, okay, let me open another file. Before we are using the software, you need to try, yeah, to get the idea using your hand. Okay, work manually first, and then you can see the idea. Okay, so let us apply bisection method. Okay. Okay, find the root of fx equal x cubic minus plus, ya, 4x square minus 10, ya, in interval in 1,2 using bisection method. Okay, so let us apply the bisection method. Yeah, what we need to do is find P1. Yeah, okay, now step 1, n equal 1, n equal 1. Okay, let a1 equal 1 and a b1, yeah, b1 equal 2. Then p1 is a1 plus b1 over 2, or 1 plus 2 divided by 2 is, it's 3 over 2. Yeah, okay, now you check. Previously we already have fa1. Yeah, fa1 is how much? Let's see. fa1 or f1 is, minus 5. Yeah, minus 5 or negative. And fb1, sorry, is f2 equal to 14. Yeah, positive. Now check fp1. fp1 is f3 over 2. that is positive or negative. Okay, so you can, do you know Horner method? Yes, to apply this. So you don't have to, okay, normally you can calculate like this, 3/2 square plus 4 times 3/, oh sorry, cubic square minus 10. So this is the normal way, yeah. But we can apply the Horner method. How the Horner method work? It work like this. Okay, so look at this. So we start with x power 3, yeah. So the coefficient of x power 3 is 1. We put 1 in here. 1. Coefficient of x/2, continue to x/2 power 2. The coefficient is 4. Yeah, we put 4 in here. And then coefficient of x power 1. There's no coefficient. There's no x power 1 in here. It means that the coefficient is 0. Yeah. And the last is the constant is -10. Okay, let's check. If x equal 1, you just put in here 1. Yeah. And then derive. Okay, you can put 1 below here. Multiply with 1. Yeah, 1 times 1, it's 1. You put the positive sign in here. 4 plus 1, 5. Okay. 5. Okay, 5 times 1. 5 times 1 is 5. Plus again, 5. Yeah. 5 times 1 again, it's 5. Okay. Now minus 10 plus 5 is minus 5. Okay, so look at this. This minus 5 is the value. Yeah. Same with like we have before. Okay, so it's easier. See it. So this is the value of f1. Okay, let us apply for 3/2. Okay, let us apply for 3/2. Okay, I will erase this. Can you check that? So in here, 3/2. 3/2. Okay, 1 times 3/2, we have 3/2. Yeah, then 4 plus 3/2 is 11. Yeah, 11 over 2, right? Yeah. So 11/2 times 3/2, we have 33/4. Yeah, multiplication. And then 0 plus 33/4 is 33/4. Do the multiplication again. We have 99 over 8. Yeah. Then we have in here how much? 19/8. Yeah. 19/8. It's positive. So this is f3/2, a positive. So now look at this. Because fp1, yeah, fp1 is positive, have the same sign with fb1, which is also positive. Then, yeah, we remove b1. Okay, because here, because fb1 and which is f1, yeah, which is f1 and sorry, f2 and fp1, which is f3/2, has the same sign, then we remove b1. Yeah, b1. Okay, so that is the first iteration. Now we are looking into the interval a1. Yeah. Okay, now we are interval. Now we are in A1, P1. Okay, so this is the interval that contain the root. Okay, so that is the first step. Yeah, then continue to n equal to the second iteration. N2, n equal to. So you have, let A2 equal, yeah, this one become A2, yeah, A1, which is 1, and B2 equal P1, that is 3/2. Then find P2. Then P2 is equal to, yeah, A1, yeah, B2 or A2 plus B2 over 2. That is 1 plus 3/2 divided by 2. Okay, so you have in here how much? 7, no, 6, yeah, 5. 5/4, yeah, 5/4. Okay, hello, can you follow me?
Yes, sir.
Yes, sir.
Now you check P2 using Horner.
Yes, sir.
Can you check that? Check P2 using Horner. We have now, yeah, you already know, F1 is -5. F3/2 is 19/8, yeah, 19/8. Then check FP, F5/4. Using Horner. Anyone has finished? 5/4. This is 1, 4, 0, 10. Yeah, 1, 5/4 plus in here. Anyone can calculate this? How much result here? What is 4 plus 5/4? Yeah, you can use microphone. Yeah, 21/4. Okay, you do the same, yeah. It is 105/16. And then you can calculate in here is the same. And then you have 5 to 5, yeah, over 64. Okay, so you have in here positive again, right? Oh, this is negative, sorry, this is -10. So negative in here, yeah, negative
115 over
100 berapa? 15.
ya.
Okay, good. Thank you.
64.
Over 64. And negative, yeah. So this is F5/4. Negative. Then you know what to do? Remove which one? FP2 have the same sign with FA2. Yeah, remove this one. Okay. Because F A1, which is F1, and FP2, which is F5/4, okay, has the same sign, then remove A2, yeah, remove A2. Now we are in interval 5/4 until 3/2, yeah, okay. Now we are in interval 5/4 until 3/2. Okay, so you continue the third step, yeah. You continue the n equal 3. Okay, so it's repeated, yeah. It's repeated. Therefore, you can create the following. You can create the following table, yeah, containing the result that we have. Yeah. So now, first we have n. Yeah, create a table n, which is number of iteration. An, Bn, Pn, and then Fpn. Okay, so currently we have n equal 1. A1 is 1, B1 is 2. Okay, P1 is 3/2. Yeah, P1 is 3/2. Like, okay, so this one is 3/2. And FP1 is 19/8. Yeah, 19/8. And equal to, you have A2. What is A2? So A2 is 1 and B2 is 3/2. 1 and this one is 3/2. And P2 is, okay, P2 is 5/4, yeah, 5/4. And then F5/4 is, see, 19, sorry, this one, minus 115/64, minus 115/64. Okay, you can continue again, yeah. So in the next step, we have 5/4 for A3, and B3 is 3/2. Yeah, and you can calculate what is the value here and what is the value here. You get it? Hello? Yeah, so it's repeated, yeah, until step 4, 5, and so on. Now let us see using the Python, yeah. So to save time, I have write the code here. Let's see the bisection method. Oh, this is Newton actually, not bisection. Oh, I made the mistake here. Okay, so this is not bisection. Bisection starts afterwards. Okay, so this is the bisection algorithm. Yeah. What you need to do, input two value of x that embrace the interval where the root is expected. Yeah, so this is find the, okay, you put the interval a and b, yeah, or a1 that will become a1 and b1. Corresponding calculate corresponding value for y. Yeah, you calculate fa1 and fb1. check the sign between the difference between y value. Okay, what is the sign of FA1 and sign of FB1? Okay, and then if the sign are not opposite, stop. The program still stop. It means you need to repeat to the step 1. Yeah, find the value again. But if the sign is different, you can continue to step 5. Calculate the value of x in the half of the interval. Yeah, and then you check again the sign difference between y value in the first half. Yeah, if the sign are opposite, let x1 and x2 be the limit of the first half interval. Okay, so this is the okay, this is the step. Yeah, so look at this. You need to use if. Yeah, you need to use for and if. Yeah, this is the what is called. Yeah, this is the if statement. Yeah, if statement. Check the sign different. You always repeat. Okay, let's start with input in here. So I will use the same. Yeah, I will change. The previous problem is x cubic plus 4x squared minus 10. Yeah, I will change this. X cubic plus 4x squared, yeah, minus 10 equals 0. So we don't have analytical solution in here. We do not know yet. Okay, find roots of the following equation. Now, input the two value of x. Yeah, so we have x1 or a1 in here, yeah. In our previous, x1 is 1, x2 is 2. Okay, and then you need to calculate the corresponding value. This one is y1 or fx1, yeah, or fa. Put the interval here. You multiply. Okay, so you put here, yeah, x1 power 3. So in Python, power you put here like this, star star 3, and then we have plus, yeah, plus 4 times x star star 2 power 2, okay, minus 10, yeah. So this is the value, yeah, fa1. Copy this, change this one become 2. Sorry, this one x1, this is x2. Okay, so now you have this. Now this is how the algorithm works. Yeah, we check the sign. If y1 times y2 positive, what does it mean? It means that if they are positive, it means they have the same sign, right? Negative times negative, also positive times positive is positive, right? Therefore, you need to repeat to step 1, which is change the interval guess. Yeah. So look at this. Print root. The root is not within the given interval. Okay, and then exit. It means you need this program stop. However, if this requirement or this condition is not satisfied, yeah, which means y1 times y2 is negative. So if the multiplication of two number is negative, then the number has different sign, yeah. And then you put this. Okay, so then we need to change the following. So for now we will repeat, yeah. So look at this. For I in range 1 until 101, it means we are repeating the step until 100 iteration, yeah, until 100 iteration. We use this one, x1 plus x2 divided by 2. This is the point, yeah. This is the point that we have. And then we calculate the value of function in the following, in the new point, yeah. Okay, so I will put here x h star 3 plus 4 star x1 xh star 2 minus 10, yeah. And then the same, y1 in here is the same, yeah, x1 power 3 plus 4 x1 star 2 minus 10. Okay, this is wrong. Okay, now check is if absolute value y1 lesser than 1 minus. Okay, so what is y1 here? What y1 is the difference in here, yeah? Okay, so we want to check the value here, yeah? We want to check the value. It depends on what kind, how much you want, yeah? It depends on how much, or the accuracy that you want. So I will give this as 0.0000 until power minus 6, yeah? It's really, really accurate. Yeah, if this condition is satisfied, okay, break it stop, yeah. If this condition is not satisfied, and then we can continue the following, yeah. Now look at this. If y1 times yh, this is the bisection point or in center point, yeah, lesser than 0 or negative, use this x2 equal xh, yeah, else x1 equal xh. Yeah, so this is, it will give us if it will choose which one, yeah, which one is the new point, yeah, the new a1 or the new b1. Okay, so the new b2 and so on, yeah. And then print the result. Okay, let's check. So look at this, the root is 1.36523, yeah, the root is 1.36523 with the number of bisection is 24, or there are 24 iterations in here. Okay, yeah, so I will give this to you as the exercise, yeah, in your home. So I will not repeat what is Python and how to calculate, yeah. But if you already know that, it will give you the advantage, yeah. Yeah, make sure that you know how to process this. Make sure you know how to process this. Therefore, we can calculate. If you want to have a more, let's say, accuracy, yeah. So it will give the program, yeah, how long he will work. Let us give more accuracy, like it's really, really more accurate, yeah. Let's give 10, okay. Now let's see. In IPython notebook, if you want to run the program, press Shift Enter, yeah. So look at this. The root is 1.36523. Number of bisection 36. Okay, you can try. Let us calculate. Let's say P is equal to 1. Let's check, yeah. 36523. Okay, and then I want to check the value, yeah, or the value of a function when P equal this. Okay, yp equal to P power 3 plus 4 times P power 2 minus 10. And then let's see yp. Oh, is that something wrong here? Is there something wrong? You see that? Why the result is -2? Oh, look at this. it's minus 2 power e power minus 0.7. It's really small, yeah. You see, it's really close to 0, yeah. It's like 0.1234567 2, yeah, like this, minus. You see, that's how the program works, yeah. And if you want to have more accurate, like minus 20, yeah, you just put here, enter. You see bisection 50, yeah. And then let us put p now 1.36523 36523. I think it's the same, yeah. Yeah, it's the same. So it's converged to this value, yeah. Even you add more points, so it's really small and really close to 0 because it's power minus 10 and minus 7. Okay. Any question?
No, sir.
Can you try this later? Yeah, in your home. Okay. So that is bisection method. Yeah. That is bisection method. Now let's continue to the next. Yeah, that is Newton. Okay, so before we continue, this is the guarantee of bisection method. If f is continuous, yeah, with the following requirement, the bisection method generates a sequence of point Pn, yeah, approximating the value of 0 with, yeah, this is the error approximation, yeah. This is the error approximation. This theorem guarantee that the procedure that we perform, yeah, will converge. And this is the rate of convergence, okay? This is the rate of convergence. As you can see, if you add more iteration in here, so the power or the divider in here will be bigger and bigger such that the error becomes smaller and smaller, right? Yeah. So yeah, how this is how fast, yeah. It's guarantee how fast the algorithm or the procedure will converge to the root, yeah, or to the point that we want to find. Yeah. Okay, this is the important theorem. So it's like when you offer some method, okay, someone will ask you, how good is your method? Okay, yes, it works, but is your method is reliable? Okay, that's the next question. If your method is work, now is your method reliable? Okay, then the next question is how good is your method? So this is it give the guarantee. Yeah, as you can see, this is order of convergence. Okay, as if you add more and more iteration, it will converge to the true value with the following error. Yeah. Okay, next, let's continue. Yeah, so look at this. This is another equation. Determine the number of iteration necessary to solve the following with accuracy 10 power minus 3. Yeah, using A1 and B1 equal to. Okay, so we already have this. You just change the accuracy, yeah. You just change the accuracy until minus 10, minus 3. Okay, so I just change this to 3 and then run the program. So the iteration is 15, yeah. We have 15 iteration. So the answer for this is 15. Okay, that is bisection method. Let's continue to Newton. So this is the Newton method. Suppose that f is f belong to C2AB. What does it mean? It means the function is continuous and differentiable up to twice, yeah, up to twice. Okay, so the requirement in here is not only continuous, but also it must be differentiable atau punya turunan, ya. Some of the function has differentiability up to n time, ya. N is depend on the nature of that function. So actually, this method is more restrictive than the bisection method. Yeah, in the bisection method, you only require, yeah, the requirement of the function is only continue, yeah, regardless the differentiability. But in here, it must be continuous and differentiable. That's the problem, yeah. It gives you more requirement, that is differentiability. Okay, let's see. And then let P null in the interval A until B, yeah. And then B approximation to P such that F prime P not 0. And the difference between P and P null is really, really small, okay. Yeah, see, this value P is the point that we want to find, and P null is the guess point, yeah, the guessing point or the starting point. Consider the first Taylor polynomial. So we perform the polynomial, yeah, Taylor polynomial of f round P null. Okay, so the polynomial will be look like this. You can see f p null plus f prime p null actually here. Yeah, f prime p null, and then this one c p null. Okay, until the second derivative. Okay, because we choose the value of p null close to p, yeah, that the distance is really, really small. Therefore, the small value square will become smaller. Consider like p minus p null has 0.1, for example. Yeah. So if p minus p null is 0.1, and then you square 0.1, the result will be 0.001, right? It becomes smaller and smaller. Therefore, this term can be omit, ya. Jadi suku ini bisa diabaikan because the term is really, really small. Therefore, we need to choose the value of p null that is hopefully will be close to our root, ya. Okay. Then, because fp is the root, ya, is 0, this equation give, so this term will be 0, and all of them in here. This is p null again, yeah. This is p null again, and then yeah, because we omit this term because it's really, really small, then we can approximate the following: 0 approximated using f p null plus f prime p null, p minus p null, yeah, remaining this term. Okay, and then solving for p. Yeah, solving for p meaning like this. You multiply this and then you multiply this, or you don't have to, yeah. So okay, so let us derive this. Is f p null plus f prime p null times p minus f prime p null times p null. Okay, what we want to find is the value of this p, right? The value of this p, and then move everything to the right. Okay, this one become positive, this one become negative, yeah, and then we have p equal to f prime p null times p null, okay, minus f p null, okay, divide by f prime p null. Okay, this one cancel in here. It remain p equal to P null minus F P null over F prime P null. Okay, so that's the steps in, or this is the Newton method, yeah. Okay, so this is the value. Okay, so basically this is the iteration, yeah, in Newton. The next point, first you start with guess, yeah, guess point in here. Okay, you start with n equal 1. Okay, you have P null F P null over F prime P null. Then you have the new value become P1. And then for P2, you repeat the same. P1, yeah, minus F P1 over F prime P1. Then you have P2. And then for P3, you do the same. P2 minus F P2 over F prime P2, okay? And then so on, the process goes on, yeah, until, of course, you need to check each step, yeah, what is the value of FP2 in here, yeah. Before you continue to step 3 like this, or from step 1 to step 2, you need to check what is the value of FP2 in here, okay. If FP2 is 0, then the process stops. But if FP2 is not 0, yeah, the process goes again until you have the desired accuracy, yeah, like 0.00 something that you want. Okay, yeah, this is the step in Newton. Yeah, you input the approximation, you start with the initial guess, yeah, and then you give the tolerance, how much the accuracy that you want, and number of iteration, like I did before, number of iteration like 100 iteration. So these two value will be depend on the which one is satisfied, yeah. If the tolerance is satisfied before the iteration finish, the program will stop. But if the tolerance is not satisfied, the program will continue until the iteration satisfied, yeah. Therefore, we use while in here. Okay. Yeah, this is the algorithm, yeah. This algorithm, you can use this to apply in your program. I will show you later. Okay, let's see the example. Consider the function fx cos x minus x equals 0. Approximate a root of f using Newton method. Okay, let's go to the notes. Okay, now we have in here Newton method. That is Pn plus, yeah, let's edit Pn minus 1 minus f Pn minus 1 over f prime Pn minus 1. Okay, this is the iteration or the steps, yeah. The problem we have, given, okay, find the root of fx equal to cos x minus x. Or solve, yeah. Solve. Okay, solve cos x minus x equals 0 using Newton method. Okay, so you can start with initial guess, yeah. Do you know the answer for this? What is the x? Or you can guess, yeah? Yeah, you can start, let's say if your x is 0, cos 0 is 1, yeah? So 1 minus 0 is 1. Okay, and you can go on and on and on, right? Okay, let us start with any suggestion? Okay, now let p null equal, you can guess, yeah? Let's start with 0. Let p null 0. Then, yeah, this is fx, yeah? This is the fx. F0 is cos 0 minus 0. Yeah, is 1. Of course, it's not positive. And then find the f prime x. F prime x is, the first derivative is minus sinus x minus 1. Okay. And then f prime 0 minus sinus 0 minus 1. It is minus 1, right? Okay. Now put into the iteration, yeah, n equal 1. So you have p1 equal to p0 minus f p0 f prime p0. Then we have 0, 1 minus 1 over minus 1, yeah. So p1 become positive 1, okay. So you have p1. Then check p1. Because before you continue, to the next iteration, fp1 is f1, right? Is cos 1 minus 1. Of course, you need to use the calculator to calculate this, yeah. Okay, you can use Python to calculate, yeah, at least as a calculator. So if you want to use Python, you need to import a package first, yeah. It's called a math package, yeah. So if you not activate the package, it will not work. Yeah, look at this. It's error, yeah. The Python does not recognize the cost. Therefore, you need to import a package in order this function to be work. Say, so the syntax is from math import star. Yeah, so it will import, yeah, all the package in mathematics. Okay, now let's put again the same cos 1. So it gives us the result 0.54030 or 0.5430. Okay, so that's the result, yeah. 0.540302. And so on, yeah. So that is the FP1, and then as you can see, it's still far from 0. And then you continue to the second iteration, n2, n equal to, yeah. For n equal to, then find, you already know, yeah. P1 is 1 and FP1 0.54302, F prime P1 or F prime 1, it is minus sin 1, yeah, minus sin 1 minus 1. Okay, so what the result is this? Okay, let's check. Okay, let's calculate minus sin 1 minus 1. See, result is minus 1.84147. Minus 1.84147. Minus 1.84147. Okay. Then you continue to find P2. Yeah. P2 equal to cos 1 belum dikurangi 1. Let's see. Which one is that? Oh yeah, it does not minus 1 yet here. Thank you. Okay, let's see. How much is that? Minus 459. Minus 45969. Minus 45969. Okay. Minus 45. Okay. Minus 0.45. 969. Okay, then you can put again here minus 0.45969. Okay, so now we have P2 is P1, yeah. P2 is P1 minus F P1 over F prime P1. So is it 1 minus, yeah, let's put the bracket, minus 0.696 969 minus 1.84147. Okay, so what's the result? Okay, so I have in here, this is how you work manually without programming, yeah. This is look like calculator. 1 minus this one, yeah, minus 0.45645 45969 divide minus 1.84147, enter. So it's 0.7503, yeah, 0.575036. Seven. Okay, so this is P2, yeah. And then again, check FP2. FP2 before continue to the next iteration. F 0.75036. Okay, so this one is cost, yeah, 0.75036 minus 1. So it's closer, right? Previously we have minus 0.4, now we have minus 0.2685, yeah? Minus 0.2685. Okay, therefore, yeah, so you will have, eventually, you can arrange your result in the form of table. Yeah, you can write your result in the term of table, and the table will be look like this, Newton method. Yeah, we have n, pn, and fpn. Yeah, first we have n equal 1. P1 is 1, okay? P1 is 1, fp1 is 0 minus 0.45969. Minus 0.45969. And then iteration 2, we have P2 is 0.750. 0.7536 minus 0.2685, yeah, 685. Yeah, it can be continue until as many as you want, right? Yeah, so I will give you as exercise. Yeah, what is the third iteration and fourth until 5. Okay, you can continue until 5 iteration as your exercise. Okay. Any question until here?
Not yet,
No,
sir.
sir.
No, sir.
Yeah, so it's your exercise, yeah? You can continue until 5 iteration. Now, let's see the program. Here, this is the Newton method, yeah? Newton or Newton-Raphson method. This is the syntax or the program. Okay, let me see the start. Where is that? Okay, so here is it, yeah? You put the initial guess in here. Yeah, we are starting with initial guess, and then you do the iteration. Yeah, for iteration 1 until 100. Yeah, in Python. In here, this is it gives you the value from 1 until 100. So in Python, 101 is the last point or the last value in here. It does not include in the range. Yeah, even you put 1 until 100 in 1, the result is 1 until 100. Yeah, the end point or the end value does not included in the range. Okay, so put x new. Look at this. This is x new or x value, the new value. This is old value x minus. This is fx or the value in here, and then this is the prime. Yeah. Okay, let us give. Let's start again for our for the problem. So the good thing about IPython, you can also create the notes like this. Yeah. You can use markdown in here. You can see you can change between code and markdown environment. Yeah. So if you change into markdown, and then press enter. Look at this. So this is in command mode. Yeah, it is not start yet. So if you want to go into markdown, you can press enter until you see the input. Okay, so let us start the problem. Solve the form, or find the solution of. Okay, and then it's also support mathematical expression, yeah, using LaTeX. So you start, if you want to put the mathematical expression, you can start with $sign and then put the mathematical expression between two $sign in here. Fx equal, we have cos x, yeah, minus 1 equal 0. So this is the symbol for cos. Yeah, you can have cos, sin, or any other mathematical symbol, and you can find the symbol in the following site. Yeah, let's say LaTeX symbol. So it will give you the following result. Look at this. You have many search in here. Okay, I will give you one of the good search is the following, overleaf. Yeah, you see, it gives you the mathematical expression, yeah, that can be applied into IPython notebook, or you can find from other source. For example, like this, Google give us the following. See, these are the mathematical symbol, yeah, that can be applied to the IPython notebook. Yeah, you can apply whatever you want, depend on your needs. Okay. Yeah, I will leave this to you as the exercise. Yeah. Okay, next, let's go back. Using bisection method. Sorry, Newton method, not bisection. Newton method. Okay. We start with the initial point here. I will put P equal. Previously we start with 0, yeah. 0. And then for iteration in range 1 until 101. Yeah, this is for syntax. Yeah, you already know this. Oops, not working yet. And then put P new equal to P minus, yeah, and then here put the FP, yeah, cos P minus 1. This is FP, divide derivative minus cos P. Okay, sorry, this is P, yeah, this is P. Minus sin in here, minus sin P minus 1. Okay. And then let us give the tolerance, yeah, if absolute value P new, the new one with the old one, yeah, lesser than 1.0 e power minus 6, it means 0.000006, yeah, there are 6 times zeros after comma. Break. Forgot the colon. Break. And then repeat the step. Our new P is P new. Okay. And then print. I think I will copy the steps. So this is P new now. Okay. Let's enter. Let's see the result. See, the iteration is 5 times. Yeah. The result is the root is 0.73909. Okay, let's check. Is it close? How close is that? Cos 0.73. Okay, P new. I think I will put with P new minus, this is P new actually, right? Minus P new. I think I will put 0.73909 minus 0.73909. Yeah, so it's result. Yeah. So if you want to if you want to know each step in here, let's say you want to know its value, each value in every step, you can print in here. Print P new. Yeah, look at this. We start with one, first iteration, second, third, and so on. 1, 2, 3, 4, 5. Yeah, until 5 iteration. If you want to have more accuracy, let us put until -10, power -10. Yeah. Okay, so it's 6 iteration, and then 20 more, power -20, 7 iteration, 50. Yeah, again 7 iteration. Let's say 100. Yeah. You see, this is the result. Yeah. Until power -100. It's really it's already converged. Yeah. This is the maximum or the closest value that computer can give. Yeah. This is the closest value to the root that computer can give. The computer cannot give more accurate than this value. Yeah, it's already power -6. Okay, you get it? Any question?
Sir, nanti file Jupyternya boleh dibagikan, Sir?
Yes, I will. Yeah, I will put in eCampus. Yeah, so you can access from there.
Okay, Sir. Thank you.
So the purpose is so you can play with this. Yeah, so you can play with this. You can try. You can change the function. I will give you the task or exercise or assignment. Yeah, what you need to do is find the root using different function. So you don't have to change this program. Yeah, so you just change the function, different problem, and observe the result. Okay, that is the assignment for you later. Yeah. Can you open that? Or if you can open that, you can try. If you can open the Jupyter Note in your computer, you can also try. Actually, it does not use the internet. Yeah, it works on your local host. Yeah, this is not using internet. This is not using internet. It works on your computer. Therefore, it doesn't need, or it doesn't take the bandwidth. Yeah, and then the program is not using a big memory like MATLAB. Yeah, because yeah, it's a really simple program actually. As you can see, in my computer, it's worked fine. Yeah, it works really fine. Different if we are using MATLAB. Yeah, of course, MATLAB has different advantage. Yeah, but I think for this course, it's sufficient to use Python. Any more question? Okay, so if there is no question, I will continue to the fixed point iteration. Yeah. So actually, you already know the most common method. Yeah, the most common method in numerical or in root finding problem, that is Bisection and Newton. And you can see the advantage of both. Yeah, so the Bisection method does not require the function to be differentiable. Yeah, however, it gives us slow accuracy, right? The Bisection method gives us slow accuracy, as you can see in the previous example. In here, yeah, it gives you many steps, yeah, like 15 steps, while in Newton it's only small step, like 7 or less than 10 steps. Yeah, of course, that is the advantage of Newton. If it gives you faster conversion rate rather than bisection. Yeah, but the advantage of bisection, it does not require the function to be differentiable. But in Newton, the function required to be differentiable twice. Yeah, if the function is not differentiable, then you cannot use the Newton method. Okay, let's continue to the fixed point iteration. Yeah. So the number p. So this is the definition of fixed point iteration. The number p is a fixed point for a given function g if satisfies the function following. If we evaluate the function at p, it gives us the result p as well. Yeah, same with the value, same with the point. Yeah, the value of the function is the same with the value of point of the input. Yeah. Therefore, if we have the following problem, yeah, let's say we want to find p such that fp equals 0. We can define function g with a fixed point at p in a number of ways. For example, we can put gx equal to x minus fx, or gx equal to x plus 3fx. It depends. Yeah. So in fixed point iteration, we can arrange many kind of expression from fx. Yeah. Therefore, we can arrange, after we arrange an expression, we can arrange iteration. Yeah. So that is the idea of fixed point iteration. Okay, so let's see the example. Determine any fixed point of the function gx x squared minus 2. Yeah. So basically what we do in here, yeah, find the point p, yeah, such that in here. So this is not the root finding problem. Yeah, This is not root finding problem because we already know this. Yeah, x squared minus 2 is quadratic and the root is square. So x1, 2, the root is plus minus square root of 2, right? Plus minus akar 2 adalah root or root of this function. If we put plus or minus square root of 2 into this function, it will give us 0. Okay, so the problem in here, find any fixed point. Yeah, so find P such that GP equal P. Yeah, or if you change P into X, find X such that GX equal X. Okay, basically you find the intersection. Yeah, you find the intersection point between this function with the line X. Yeah, this is the illustration. You want to find the point, this is the point, between the curve and y equal x. So this is the 2 point. That is the fixed point. Yeah, the fixed point. Okay, so to find that, you need to solve x equal x squared minus 2. So we have 0, x squared minus 2 minus x, right? So we have x squared minus x minus 2. Yeah, you can solve this easily. What is the result? Yeah, this is the result. Yeah, 2n minus 1. X. This is minus 2 plus 1. And x equal 2 or x equal minus 1. Yeah, so this is the fixed point. The fixed point, we have two fixed point in here. That is x equal 2 and x equal minus 1. Yeah, if you check, see here, G2 equal to 2 squared minus 2. Yeah, it is equal to 2. So that you have G2 equal to. And also G minus 1. G minus 1 is minus 1 squared minus 2. It's 1 minus 2, it's minus 1. Therefore, you have G minus 1 equal minus 1. Yeah. So that is a fixed point. So we will use this procedure to help us solving the root, yeah, or to find the root. Okay, we can arrange. Okay, so this is the existence or the theorem that guarantee the existence of fixed point iteration. Yeah, the function must be continuous, and then yeah, if the function is continuous, then it guarantees that at least the function has one fixed point. In addition, if the derivative of first derivative exists on AB, and there is a positive constant k that lesser than 1, with the following requirement, it means that the gradient, yeah, the gradient of tangent line, yeah, gradient of the tangent line of the curve of G must be lesser than k. Jadi gradien dari garis singgung kurva G sepanjang interval AB ini harus kurang dari 1 ya. Maka we have the following. There is exactly one fixed point. Jadi ada dua syarat ya. Apabila dipenuhi dua syarat ini, maka atau ya at least continuous ya. Kalau continue dia punya fixed point. Kemudian in addition, if you have another requirement like this satisfied, it also will have the fixed point ya. Jadi ada dua syarat ya. So as you can see, the function continuous is satisfied to guarantee that the function has a fixed point. Okay, next let's see the example. Yeah, we have previously example. Previously we already have this, yeah. Solve cos x minus x equals 0 by using, previously we are using Newton. Now we can use the fixed point method. Fixed point method. Okay, fine. The solution, the same function, yeah. Fx equal cos x minus x using fixed point method. Yeah, so okay, equals 0 in here. So in here you see that we have fx equal cos x minus x. If we put fx equals 0, then we have the following problem. Now, what is g in here? Okay, if you change the x into the left hand side, yeah, if you move, we have x become cos x. So finding the value of x, yeah, that satisfies cos x minus x equals 0 is the same as using the following: x equal cos x. Okay, then we have the iteration, yeah. So the iteration will work like this: iteration xn equal cos xn minus 1, yeah. So this is the iteration. You start with n what, start from 1 and start from 1 2 3 and so on. Okay, then in here x null is the initial or starting point, yeah, initial guess. Okay, x null is the initial guess. Okay, you can start with any number or initial guess that you want, yeah, so that you have when n equal 1, you will have x1 cos x null. Okay, let's say your x null is 0, then you will have x1 cos 0, yeah, and then in here you have x1 equal 1. Okay, and then you continue, yeah, and then you continue. Of course, you also need to check, yeah, whether f1, what is the value of f1? Cos 1 minus 1. Yeah, it's the same like before. And then you can continue to n equal 2. If n equal 2, you will have x2 cos x1. Yeah, so your x2 equal to cos x1 is 1. Yeah, then you have what is the x2, and then so on and on and on until it satisfies the desired accuracy. Okay. Okay, so this is the simple example, yeah. Now let's see the more complicated. Yeah, I will give you the following, yeah. This one, actually this one is not difficult if we are using analytical solution, yeah. 2x squared minus 5x plus 3 equals 0. We know that the this problem has analytical solution, yeah, that is 1.5 and 1. Okay, so to start the fixed point iteration, you can arrange you can arrange this equation become like this: x equal to x squared plus 5. Okay, let's see the derivation. We have 2x squared minus 5x plus 3. Yeah, let's say, okay, let's ask fx 2x squared minus 5x plus 3 minus 5x plus 3. And we want to solve this, yeah. Solve fx equals 0. Yeah, you know that it is easy actually, yeah. But we want to see how good, yeah, fixed point iteration can solve this problem by start with the problem that we already know the answer. So I know that this is minus 3, right? Yeah. And then this is minus 2 and minus 1, right? And then we have x equal to 3 over 2 or x equal 1. Okay, now let us apply fixed point iteration. So first we have 2x squared minus 5x plus 3. Okay, first you can arrange, yeah, so that x stay alone in one side, yeah. Okay, so the simple way is to remove or to move this minus 5x to the left. We have 5x equal to x squared plus 3, right? And then x equal to 2x squared plus 3 over 5. This is the first arrangement, yeah. Okay, and then look at the second arrangement. We can derive from this, yeah. Instead of moving only 5x, let us start or derive from this. We have 5x, or moving all the term in here, we have 5x minus 3 equal 2x squared, yeah. Or I have 2x squared equal to 5x minus 3. Then we have x squared is 5x minus 3 over 2, yeah. And we have in here x equal to square root of 5x minus 3 over 2. Yeah, this is the second arrangement. You see the difference, yeah? We have the first arrangement like this. You can choose the first. This is the first arrangement. Or this is the second arrangement. Okay, now you can apply the fixed point, yeah? Fixed point iteration. So I have write the code in here. Okay, actually you don't have to use this, yeah. So I use NumPy and Matplotlib to display the result, but in general you don't have to. Okay, you already see the result is 1 and 1.5, right? Now if I start, let's say the initial guess, I will start from 0.5, yeah. What's the result? If I start from 0.5, yeah, and then apply the following using 2x squared plus 3 over 5, yeah. This is x new, this is the x initial, and then I want to see the iteration. Let's see the iteration here, and this is the desired accuracy, yeah, or the difference between the new one and the old one. So if we are close to the exact solution, yeah, the x new and x old will be closer and closer, right? Yeah. If x, you see here, if this is x new and this is x old, yeah. If we know that it will become 0 in here, or it will satisfy the solution when x new and x old, the difference between x new and x old becomes smaller and smaller. Therefore, I put this is accuracy like this, yeah. Or you can put, so how many 0 in here? 1, 2, 3, 4, 5. So you can put the same as 1.0 e minus 5, yeah. So this is the same. Okay, so if this tolerance or this requirement satisfied, yeah, the process will be stopped. If not, it will continue, yeah, with using our x old become x new. Okay, setting the the new iteration. Okay, let's enter this, shift enter. Okay, what is it? See, this is the result, yeah. And we start with 0.5. It's calculate really long time until we have 39 iteration, and the root is 0.99997. Okay, it's close to 1, yeah. Okay, I will put this as 6. Yeah, so look at this. It need 49 iteration, yeah, to reach 1. You see? Let's put another initial guess. You already know the result is 1, yeah. You already know the exact value is 1 and 1.5. Okay, so if you put 1.2, how is it going? Yeah, so it's need 52 iteration. If you put 0.9, if this is already close, right? Let's see if give us the smaller iteration. Still, yeah, we start from 0.9. It's still need 45 iteration. Okay. Yeah, probably you can use small accuracy. Yeah, let's say the small accuracy like -3. Yeah, it's only 14 iteration, but the result is not exactly or still a little bit far. Yeah, to because we give bigger tolerance. Okay, and then if you observe, it only give us the result 1. Yeah, what about this one? Let's say, let's put 1.4. So 1.4 really close to the second solution, yeah, not close to 1. Okay, let's see. See the result still 1, yeah. Okay, let me give smaller tolerance, -6. Yeah, so it needs 61 iteration, but the result is 1, yeah, not 1.5. But we already know the result, the another root is 1.5. What about we put exceed 1.5? Let's put 1.6. Okay, exceed 1.6. Okay, it gives us error. Yeah, look at this. When we put 1.6, it gives us error. You see, the difference between the x new and x old become bigger and bigger. Yeah, it doesn't converge to the solution that we want. It instead of converge to 1.5, it gives us error in here. Therefore, yeah, that's the problem with fixed point iteration. Yeah, it doesn't give us all the solution. Okay, what about if we use the following, the square root? Okay, now I'm using the following, yeah, the same procedure with initial, okay, initial 3. or I will put initial 1.6. Let's see. Okay, let's see the print and print the result. Okay, look at this. Yeah, the result is 1.5 after following 54 iteration. Yeah. Now let us put something close to 0 or close to 1. Yeah, close to another root. 0.9 will if give us the 1 solution. Error. Yeah, so that's the problem. Okay, math domain error. Why? So look at this. We are working with square root. Yeah, because 5 times 0.9 is close to 1. Yeah, 1 minus 3 is negative. Square root negative is not allowed, right? Therefore, it gives us error. Yeah. So the problem with fixed point iteration, even the problem does not require us to have differentiability, but you need to be careful with the arrangement. Yeah, different arrangement can give you different, can lead you to different root. Yeah, can lead you to different root. Let's put so your x must be greater than 5 then, right? Because we are working with square root, your x must be greater than 1. So you cannot put x smaller than 1. Okay, let us put 1.2. See the difference? It's always converge to the 1.5. Yeah, it does not converge to 1. Yeah, that's the problem. Okay, even we are close to 1. You see here, 1.001. You see, it still converge to 1.5. Yeah, that's the problem. Yeah, therefore you need to apply both of the arrangement in here to find all the roots. Yeah, to find all the roots, you need to apply the two arrangement. Yeah, the first one always converge to 1, and the second one always converge to 1.5. Okay. Okay, any question until here? So we have covered 3 methods, yeah, in root finding: Bisection method, Newton method, and fixed point method. Yeah, you see the advantage and the drawbacks of each method. So the point is, there is no super method in this world. Yeah, there is no the most powerful method. Yeah, each method has advantage and drawbacks. Yeah, or weakness. Yeah, so that is the reality that we have. Yeah, in this world there is no perfect method that will always give us a good accuracy or a best. Yeah, until we have the exact solution. No. So the exact solution for some problem could be anything. It could be mystery. Therefore, what we can do is approximate them using the method. Yeah, but you need to keep in mind that there is no method that give the exact solution. Yeah, the exact solution is always is a mystery. Okay. Yeah, because of limitation of the computer, and our solution is in real number, where the value after comma is wild. Yeah, it doesn't have a pattern. Okay, so you can play with this. I will give you the file. Yeah, and you can play with this in your home. Any question?